Okay, welcome back to Process Dynamics and Control. Today we're going to be talking about PID controllers and specifically just an introduction to proportional only control. Okay, so PID, proportional integral derivative, we're just going to be covering the proportional part today. So we have a standard block diagram where you have a set point, you have the value that you're trying to control. Okay, that's the target that we're going to be trying to drive to that value to a certain target. And then we also have a measurement or sensor. We have an actuator as well, and then also our controller. So today we're going to be designing a P-only controller for this system. So one thing to consider is that you want your valves and sensors to respond quickly enough so that you have acceptable control performance. One thing to keep in mind is that if you have a dominant time constant of, let's say, 10 minutes, then you want something that's going to be faster than about 70% of that time constant. So something like 9 minutes of dead time might be unacceptable. But if you have a time constant, let's say of 1,000 minutes, then a dead time, the time that it takes for these sensors or final control elements to respond, that might be acceptable to have 9 minutes. Okay, so one thing to consider as well, sometimes we lump the final control element into a total transfer function with the process, and then this becomes our controller. But we talk about the dynamics of this combined system, okay? The combined system, and then our controller is trying to drive us to that new set point that we have specified. This is just a simple on-off control. This is just a heater. Now I don't know who sets their thermostat at this level, but this would be an example of somebody that has a thermostat, for example, where you have an upper temperature, okay, and a lower temperature. So this is just on-off control. And when the temperature reaches a certain critical low value, you turn on the heater, okay? And then when it reaches a certain critical upper temperature, then you turn off the heater. Okay, and if you don't have this band, if let's say you had a temperature band like this, then you might be going on and off, or on and off, repeatedly, and perhaps wear out your heater, your furnace, due to thermal cycling. So you may want to have somewhat of a band here for this on-off control. Okay, so let's see, it might be used, for example, in home appliances, furnaces, air conditioners, ovens, refrigerators, where you have just basically one level for the on control and then off as well. Okay, so a lot of cases the on-off is too limiting. For example, if you were in a car that had cruise control that was just on-off, you'd either be at 100% gas pedal or 0% gas pedal. Okay, so not practical. So we want to have tighter control with less oscillations, and that's where this new proportional control comes in. We have a full PID equation here, and if you look at just the proportional part of it, you just take this term. Okay, so you have an error, which is the set point minus the process variable that you're trying to control. And that error, as it increases, then you add additional final control element output. Okay, so the output to the final control element. We'll also be covering in other lectures this integral term, so you integrate the error, and then also a derivative term, where you take the derivative of the process variable. Okay, so y is also the process variable, and we'll be covering that in future lectures. But today we're just going to be covering this proportional term. Okay, so one thing to keep in mind with proportional control is that if your system is non-integrating, then you're going to have, in many cases, a persistent offset. Okay, where the process variable is never going to reach in steady state the final control value. Okay, but one thing to consider, this is not like on-off control, but your controller output, or let's say this were a furnace in this case, that you could have the furnace on at 60% rate, firing rate, or 57%. So you can have intermediate values between on and off. Okay, in this case, this is a valve, and many of our examples are going to involve valves. And this, for example, is a level that we're trying to maintain, and our red is going to be the set point, and then our black is going to be our PV. Okay, so we have this measurement. The computation is going to be this controller with this P-only controller, and then control action is going to be sent to the actuator. Okay, so the goal, the objective of these controllers are to eliminate the controller error by making the measured level equal to the set point. Okay, so we have this P-only controller, okay, and it has really two items here. One is the controller bias. Now this is the value of the manipulated variable. You can set that for kind of your steady state conditions that you want to achieve. So let's say you're driving down the road at 60 miles per hour and you have 40% gas pedal and you turn on your controller. Most times the U bias is just the value of the final control element when the controller is turned on. Okay, so when it starts to control, is turned on. So in this case, the controller bias would just be 40%. And then let's say you increase the set point. Okay, so the air is going to be the set point minus the PV, that's your current speed. Okay, and let's say you increase to 65 miles per hour. Okay, now you have an error of 5, and let's say your gain is, controller gain is 2, then it means that, let's just go ahead and calculate this now, U equals 40% plus 2% per mile per hour error. And then let's say we have 65 minus 60, and then that is going to give us a new value for our gas pedal of 50%. So it said, when we wanted more speed, then it asked for more gas pedal to our car. Okay, so the controller gain will also have units. Okay, so in this case, for level control, it might be percent per meter air. In other cases, it's going to have different units, but that does have units. Okay, so we want to design a controller for a particular process, and one of the ways that we do that is to develop a first order plus dead time model that involves the three parameters Kp, Tau p, and Theta p, and then tune your controllers, at least a good starting point, based on those Kp, Tau p, and Theta p. Now, real processes are going to be nonlinear, meaning that depending on the level of operation, the Kp, Tau p, and Theta p are going to change. So sometimes you have to design the controller for the region of operation that you're interested in. Don't just design it for just any nominal values. The other thing to consider is that we have. Let me just go on to this next slide. We only have, in proportional only controller, we only have one tuning parameter. Really, it's just Kc. Okay, so if the Kc is small, the controller is going to be sluggish or not respond as much to an error. But if the Kc is large, the controller is going to be aggressive. Okay, so the way to obtain a good starting value, one way to do that is to obtain a first order plus dead time model and then have that guide the selection of Kc. So some of these, for example, ITAE controllers, okay? So if you're doing set point tracking, if you know your set point is going to change a lot, okay, then, so that might be your process variable and your set point, then you may want to use this correlation to give you a good value of Kc based on Kp, Theta p, or Theta p and Tau p. Okay, and then if it's disturbance rejection, if you expect your set point to stay constant, but there's going to be things that drive you away from that set point, then this might be a good correlation to use. Okay, ITAE is actually the integral of the time-weighted absolute error, and there's more information in the textbook about that. Okay, so correlations. You can get a best correlation. One of the correlations I like to use for just a quick back of the envelope calculation of Kc, and this works very well in most cases if you just take the inverse of Kp. A lot of times that'll get you very close. Okay, but then once you get that initial value, you're going to want to tune it. You're going to want to adjust it either up or down to get acceptable performance for your process. Okay, so let's see. We already covered this, this thought experiment on the gasoline for the car engine. I'll just go ahead and skip over that. One thing that we do need to cover is reverse acting versus direct acting. So reverse acting, now the way I always remember it is that it is counterintuitive. Okay, so you think about what makes sense, and then it's the opposite. Okay, so if Kp is positive, then the controller that we want to design is reverse acting. But if the Kp is negative, that's our process gain, then we'll want to design a controller that is direct acting. Okay, so negative Kp and Kc, that is reverse acting, or sorry, positive is going to be reverse acting, and then negative is going to be direct acting. Okay, so most times when you enter in tuning values into industrial control systems, you will always enter Kc that is a positive value. But if it's supposed to be negative, okay, just the absolute value of Kc, but if it's negative, then you'll also specify direct acting. So you'll put in a value of Kc, and then you'll say that it's direct acting versus reverse acting. Okay, so if you have negative K sub c. Okay, but if you have a positive K sub c, then you're just going to put in a positive value of K sub c and say that it's reverse acting. Okay, so anyway, let's go into the advantages of P-only controller. It's very simple to find a tuning parameter. It's only one tuning parameter, but the big disadvantage is that offset. Okay, so offset, again, if you're controlling this, it'll come up to a persistent value that's away from the set point, and we call that the offset for our system, and it'll continue like that. And that's why we have the integral term that we'll cover in the next lecture. Okay, so let's see, how do you get rid of offset? Like I said, use a PI controller versus a P-only controller. Here's an example of offset. We have the set point coming up, the controller comes up, oscillates a little bit, but then comes to a steady state value. If you increase the gain more, you're going to increase your oscillations, but it'll settle out at a lower amount of offset away from the set point. Okay, so it's a more aggressive controller. It's going to take a more severe action for any error that's there. Okay, in order to achieve the bumpless transfer, we also call this bumpless transfer. You want this U bias equal to the controller current output when you turn the controller on. Okay, so that if you're programming your own PID controller, you want to make sure that you put in some logic there, or be able to initialize this U bias value so that you don't have a bump right when you turn on the controller. Okay, that is it. And so tune in next time for the proportional integral controller that we'll discuss in the next lecture.